Let's see what else we get to do. Oh, looks like we're solving a whole bunch of equations without using a calculator. Just put that off and put it over there for now. Solve each equation. It's expected that some solutions will be expressed using log notation. Remember how we talked in class maybe about how there are rounding times that we can go to 3 decimal places, and there's times we're going to need to keep it in log notation to be exact. So, you know, we're just going to try to get exact if we can, and if we can't, then we're going to stop and just leave it in log form. That's all that that's telling us. All right? So we need to figure out that 10 to some exponent equals 10,000. I feel like we've done this problem a couple times. But let's see, 10 times 10 is 100, times a third 10 is 1,000, times a fourth 10 is 10,000, or by now I'm hoping that you know you just count the zeros. It would be 10 to the fourth, and so x has to equal 4. Number 2, we're doing 5 times 10 to the x. Now remember, please excuse my dear Aunt Sally, or PEMDAS. It's telling us that we need to do the exponent before we do multiplication. So when we're undoing it, we need to do the multiplication and then the exponent. Okay, so remember we can unwind. This exponent is only applying to the 10. So we can divide both sides by 5 to cancel out that 5 there. 10 to the x equals 100. Well, let's see. How many times do I need to multiply 10 by itself to get to 100? That's telling me it's going to have to be a 2, because 10 times 10 is 100. Alrighty, this one we have the variable in the exponent, and then we're adding 3 to it. So I need to think first that this 10 raised to the x plus 3 equals, how can I write 10,000 as a power of 10? I'm going to go steal my answer right up here. Looks like we wrote it up here as 10 to the 4th. We can do the same thing here, 10 to the 4th power. Now, maybe when we were playing log war, you remember that if the bases are the same, the exponents also have to be equal. So we need x plus 3 to equal 4. That x has to be 1. There's nothing else it can be. So if we have 1 plus 3, 10 to the 4th power, we would get 10,000. Keep on working through some of this. I'm not going to talk through every single one, but I'm going to keep on thinking about this. We already know 10,000 is 10 to the 4th. So 2 times x has to equal 4. X has to equal 2 on that one. This one I can't get to an exact value without using a calculator. So if I can't get to an exact value, it said we might be expressing it in log notation. So let's just log roll this thing over. Let's leave the x all by itself. That's our goal, is to solve for x. It's base 10, so I don't even have to write anything other than log of 315. The urge right now is to grab my calculator and get that to a decimal, but we have an exact value and we are all set to go. This one, it's tempting to grab the calculator. Oh, it's so tempting. Now that we know, we can just kind of log roll this and type in log 4,000 and then divide that, whatever we get, by the 1.2, but we gotta go in steps here. So I'm gonna log roll this. We're left with 1.2x on one side of the equation equals log base 10, so I'm just gonna keep it as log of 4,000. Now the log of 4,000 is not an exact value that I can calculate. I would get some kind of a decimal going on there. So if I need to keep this in exact, there's only one more step I can take, and that is to get the x by itself by dividing both sides by 1.2. So that's going to be our final answer here. X equals log 4,000 divided by 1.2. Remember, the exponent only applies to the base, so I can divide both sides by 7. Cancels out the 7. If I need it to equal 10, that has to be to the first power. Now I've got two exponents that have to be equal because these two are in the same base. Same base, equal to each other, same exponent. So 0.5x equals 1 because the exponents have to be equal. I'm going to divide both sides by 0.5. This is where that intuitive thing comes. If I have 1 divided by 0.5, you guys might remember this as copy dot flip-flop. So instead of 1/2, I've got 2 over 1. This equals 2. Should be boxing in all my answers there. So 1 divided by 0.5 is 2. I always think of this, if it takes like one Band-Aid to cover half of a wound, if I want to cover the whole wound, I need 2 Band-Aids. Keep plugging and chugging, friends. This time we have a base E. E, remember, is 2.71828182818281828 forever and onwards. So I certainly can't get exact when I'm looking at that as a base to something. All I can do is log roll that to get x by itself. Remember, log base E, natural log, ln of 8. And last but not least, number 10. We have an exponent, but we can divide both sides by 10 first. $250 divided by 10 is 25. Log roll that E base to the other side. 3x equals the natural log of 25. Last step though, gotta get x by itself. We're not done until x is all by itself. So x equals natural log of 25 divided by 3. Check your answers, make sure you've got them right. There is a little "Are you ready for more?" over here. And we can do those guys too, right? We can always stretch ourselves. 10 to the n equals 16 and 10 to the n equals 2, and to express them as logarithms, just log rolling. N equals log base 10, but I already know base 10 is log without needing to write it. Log 16. So if I'm looking at these two and I'm trying to figure out a relationship between these two solutions and how we know, that's an interesting question. When I start looking at these two values, right, I notice a relationship going on between these two. I have 10 to some power equaling 16 and 10 to some power equaling 2. But these two are also connected to each other. If we look at just the values of them here that we have, the 2 and 16, I can think of this like 2 to the first power. And I can write 16 also in terms of a power of 2. 2 times 2 is 4, times 2 more is 8, times 2 more is 16, so that's 2 to the 4th power. So the fact that we have these two ideas here means that they're going to be somewhat related to each other using these kinds of exponents. And so this one I actually am going to pull in my calculator and see what's going on about the relationship between these two solutions. Because if I look at the log of 16, and if I look at the log of 2, interestingly enough, they're 4 times apart from each other. You see this? How I could take the log of 2, multiply it by 4, and get to the log of 16. And that's because they have the same exponents here, n and n, but we see the exponents here, what they're equaling, their values here. This one's 4 times as much. So if I took this log 2, multiplied it by 4, we would have 4 times that n going on up here as an exponent. It's kind of a stretch, but it's kind of neat to see those kinds of relationships going on and how we can start to see those values. So it all comes from this being 4 times as much in that exponent, the values that we're looking at, that 16 equals 2 to the 4th power, that 2 equals 2 to the 1st power. So this exponent, which we know as n, will be 4 times as much. So, just kind of a neat thing to think about. Alright, so we can solve these algebraically. We did an entire 10 problems without using a calculator at all. That's pretty cool. If you have some extra time, some practice problems where you are solving some more of these things and checking them out. Thanks, friends.